So now, finally, we're actually going to get to the method or the direction within XAI that I think is most promising and most exciting these days. So I really look forward to telling you about this. And I also hope, of course, that you'll come later and tell me, or in the questions, and tell me what you guys think about this, because you, of course, have a more, you have fresher eyes than I have on this topic. So, okay, so there is one theorem that basically tells you that no post-processing of information can add information to data, okay? So when you put data into a neural network, the neural network cannot add any information that is not already in the data, okay? That's nice because that tells us that the model prediction can only rely on information inside the data, and probably we can make this is not an actual graph, this is just a mental depiction, but we can say something like the highest amount of information is going to be where the data goes into the neural network, and the neural network, or any machine learning model, or any post-processing algorithm, what it does is that it kind of funnels out, or it extracts information from the data. And the question that we're really answering when we're doing XAI is, okay, so what from the data? Like which correlations, which connections, which part of the information in the data is the neural network extracting? And I think that is kind of a very appealing way of looking at it. And according to the minimum description length principle, one view on learning is just that comprehension is compression, right? When you understand something, what you manage to do is that you extract, or you just compress information into what is valuable to you, and you disregard the rest of it. You disregard the noise, kind of. And when you comprehend something, you're able to express it in a much smaller length than what it took to basically to describe everything that went in, or the full data, which I think is a very kind of elegant and like appealing way of thinking about what machine learning models do. So for this final method that I'm going to tell you about, let's enter it with the question of what part of the information from the data is the model extracting. And now I'm a bit nervous about showing this slide on camera, because what I did was that I saw a presentation by a researcher called Bean Kim, who is behind the method that I'm going to tell you about. And this slide in a presentation for me was just kind of so illuminating, so good at describing this that I screenshotted it and pasted it into my presentation. And I don't know if I'm allowed to do that, but I'm an academic and we're a bit stupid. So, okay, so this slide here is from a researcher called Bean Kim, and I hope I'm allowed to do this. But okay, what we see here are two images that have been predicted upon by an image recognition model. And what we see in these images are various different things, right? There are ATMs or cash machines, and there are people in both images, but one was classified as a cash machine, and the other, the bottom image, was classified as a sliding door. Now, the question that, for instance, saliency maps or image map or whatever can't answer for us here is which elements, or not which elements, which concepts inside these images actually contributed to each of these predictions, right? Because if we try to make saliency maps here, the model is going to be like, yeah, a bit there and a bit here, and you know the edge there and that shape. But that doesn't really tell us like which concept, which integral information building blocks went into these predictions. You know, why did it become cash machine on top, not on the bottom? Because many explanation methods cannot produce information using symbols or concepts that are not features of the input data, okay? So if you have an image that you send into an image classification model, then it doesn't say literally on the image, sliding door, ATM, person, or whatever. It's just the pixel values, it's just the numbers, right? Well, the model may have understood that there are things in the world like sliding doors and ATMs and people, and I would like to know whether the model makes use of such concepts. And I want those words, those concepts, to be part of the explanation that I receive from the model, right? That is the dream. And the wonderful thing is that we're now living in the time where we can receive explanations that make use of such concepts. So that is the principle behind concept activation vectors. That was introduced in a paper where this researcher at Google, Bean Kim, was the first author, and she got a prize for the paper and everything. It's absolutely wonderful. So the good thing is that we can actually probe neural networks to find out which concepts it is that they have modeled. So a question that I could, for instance, ask is, okay, so I have this dog here, a Dalmatian, that goes into a non-interpretable model, so it can be a CNN, and I can ask, how much did the concept or the pattern dotted influence the prediction? Was it important for the model that this dog is spotty, that it has dots? Right? So how can I do that? How can I find out whether the spotted pattern of the dog was important for the classification that the model did? So what I can do then is that I can assemble two data sets. These are going to be my concept detection data sets. So I have to carefully select them. So one of them is going to contain loads and loads of examples of dotted stuff. Okay, so I can even sit down and just make like these pictures with just dots on them, or I can collect images with dotted stuff. And then I want to have one, so that's like my positive concept data set. That's the data set representing the concept. And then I need one data set without dotted stuff in it. Like, so all the other stuff in the world can be represented in that data set. So I have a positive and negative concept data set. And then what I do is that I put those, or I send all of those data points from the two data sets through my model, and then I collect the activations of each layer throughout the model. Okay, so we're just going to look at one layer here, index L. It has some dimension M. So what the neural network then does is that it goes from the n-dimensional feature space where the images live, they have n dimensions, and then it transforms this data by passing it from layer to layer to a layer that lives in a dimensionality M, right? So I've sent the images to some other values, and the numbers I get out here are the activations of layer L, dimension M. Now what I can do then, I sit there with these activations. Some of the activations I got from the concept positive data set, some of the activations I got from the concept negative data set, and then I can ask, from these activations here now, can I train a linear classifier that manages to separate the two? Okay, so is there sufficient information here to make a linear classifier where kind of the dotted stuff represented by layer L is on one side and the non-dotted stuff represented by the layer is on the other side? And if I can do that, then that means that the neural network has represented this concept of being dotted in a very simple way, right? Because the most simple way you can separate data is linearly. Right? So if this happens, then I have a concept activation vector, VL sub C, L because it's at layer L, and C because it's for this specific concept, so in our case, dotted. And that also means that the farther away I go from this decision surface that lives in this m-dimensional space, the more I move into or away from the concept that I was probing for. Okay, so I'm going to get a different VC for each layer, and for each concept that I can think of, I can make these concept activation vectors. Okay? So this sounds really abstract, but I'm really just asking whether the activations in a layer, so the way that a model represents information inside one layer, can be used to separate concepts. All right? And if it can, then that means that the neural network is using its resources in order to understand or to model this concept, okay? And then what I can do is that I can differentiate predictions with respect to the concept activation. And what I'm asking then is, how much does this concept affect the prediction of the model? Okay, and if I do that throughout the model, from the first layer to the last layer, then I can find out how much the importance of a concept kind of propagates through a model. So from the beginning all the way to the end, like how much is this concept here the information that you've deemed worthy of preserving from the data as it travels through your model, okay? And a tell me if I'm going too fast. I just want to get through everything. And my favorite paper from 2022, which I really encourage you to read, was written by, did Ulrich give a presentation last week? Ulrich Paquet? Ulrich. I'm pronouncing it wrongly, haven't I? Ulrich, he gave a presentation last week, right? Yeah. So he's one of the authors on that paper. Did he talk about AlphaZero? No. Okay, so there's this wonderful paper out there. Basically, what the AlphaZero gang did was they sat down with a grandmaster in chess and they said, let's find out what chess knowledge AlphaZero ends up with. So they sat down and they made this list of more than 100 chess concepts, and a chess concept can be something like you're in check, or you have a queen, or you're missing a queen, or you're, yeah, I don't know. I don't play chess. You can probably tell, right? So they made a list of chess concepts, like, are you in check? Even I understand that. And then they made this concept data set, concept probing data set, where half of the data set represented the chess concept, like in check, that they were interested in. The other half was just random chess positions. And then they found out how much a model would pay attention to these different concepts throughout learning, right? Because when you do reinforcement learning, you can really like see how does a model develop while it trains. And then they did this concept activation testing or concept probing that I told you about. They did this, and then they plotted how much of the concept was present. So to how high a degree can we use the activations inside layers to linearly separate concepts to see what AlphaZero was learning during training. So when did AlphaZero understand that you have to pay attention to whether you're in check or whether your queen is gone or whatever? And I think that this is kind of the closest that we're right now getting to understand, like, how do neural networks like think? How do they conceptualize their knowledge? Unfortunately, the only negative thing that I have to say about this brilliant paper that you need to check out the archive version. It's 69 pages of pure pleasure. The only negative thing you can say about that is, of course, that AlphaZero isn't publicly available, and chess is a 64-dimensional problem, and I've tried together with students to kind of to train reinforcement learning models that play chess and then do concept probing inside them, and it's an absolute nightmare. Like, we didn't have enough computing resources at our university. So what we did then, which I couldn't have done because I'm not as smart as my students, was basically we made a little chess environment where you can play chess in the dimensionality that you want. So you can make your little reinforcement learning agent play like 5x4 chess and stuff like that. And then we published the code for that. So this is an environment where you can go and train a reinforcement learning agent on chess in the size that you want, and then you can do concept detection also, and then you can see throughout the learning what your little chess agent is, what kind of knowledge it's acquiring when. So if you want, you can scan the QR code, and you can try this environment yourself. It's really easy to use, and it's so lightweight. And if not, just check out the slides afterwards. All right, so that was actually it for methods, and we have a question. Do we also have a microphone?
Thank you. Does this also capture, I call it concept interactions, because like sometimes a concept itself is like a feature, not super informative itself, but like really would play with others, and that would make the decision in the end. Do you know what I'm getting at? Sort of, it might be relevant that I'm in check, but I can also put my opponent in check the next step or something like that.
I think if you wanted to use the methods that exist right now, you would have to then represent the combined concept in your data set. You would have to go, I'm in check and in one position, the other guy is going to be in check, and then these positions are the ones that I'm going to probe for. Okay. So that's like from the top of my head what I would answer. But then, again, I don't know, if you let me think this evening, I might have something clever to say tomorrow.
Sounds good.
Yeah.
Thanks.
More questions back there? Yeah, so if you do have questions about methods, then just kind of shoot them now if you want.
So since I can imagine that you cannot come up with infinitely many concepts, don't you think that it's a bit constraining that you have to decide which concepts you're going to do? So maybe the model was looking at something that you're not even thinking of, so it's kind of dependent on what the researcher decides.
Yeah, definitely. You can, like the way it is now, the framework allows you to test for concepts that you're able to think of, right? And then there are, of course, two questions. The one you're asking is, what about concepts I can't think of? And the other question is, of course, what about non-human concepts? So concepts that we don't have. Can we ever check for them? And then I would say that we're quickly going to encounter like dimensionality curses. Like there are so many potential concepts out there that the model could be making use of. And if we aren't able to represent them even, like then how would the data that represent them look? And would we be able to extract the concepts even if we were like staring directly at it? I know that there are some suggestions in this concept detection in AlphaZero paper, or not suggestions, more like ideas or how to approach this. But I'm not aware right now that there is anything in the literature that has like a good strategy of how to find non-human concepts, unfortunately. So that's your future Nature paper, if any of you come up with something. And I see that there's a question in the back, right? Yes. Oh, by the way, if you come up with something, you call me first, right? And then Nature. Okay, yeah, deal.
Thank you very much. But a question that I have is, so if you look at, so you will be able actually to determine per layer what the activations are. So would you be able to pinpoint which concepts are in which layer? Is it, or is that, that's the first question. Then the second question that's kind of like onto that, would you be able to determine sequentiality? In other words, would sequences be able to, sequences of concepts also be able to determine from this technique? In other words, kind of like, can you do time series analysis on this?
Okay, so first question first. Yeah, so you decide which layer you test, right? That's the layer whose activations you extract. And whether or not the concept is present is basically just determined by whether you can make a classifier that classifies into the two predefined concept classes based only on the activations inside that layer. Okay, and if you can make a linear classifier that separates them, then they are like as clearly represented as they could possibly be. And the second question, I didn't understand, but that's probably because I haven't worked with time series. So I don't know, I would like, my guess would be as good as anybody's guess, I'm sorry. All right, we can, one more question, yes? Over there.
I'm just curious about the concept you showed with the dots, example. Isn't it a potential problem, like there is many various characteristics common for the data set you selected? Like they are not only dotted, but also have 4 legs or something. Or even
no,
in
the
anything.
does not 4 legs.
Yeah, I mean, in this case not, but I mean, you can't even imagine what is a kind of common characteristic which may exist, but you don't know that.
Yeah, cursed dimensions, yeah. So if you want to be absolutely certain, I would say make an artificial data set with just dotted pictures that kind of don't have any other properties than the dots to them. Yeah, but of course, yeah, no, you can never be safe. I mean, that is one of the problems. Now I'm going out on a limb. I need to stop myself. But that is one of the problems with AI safety, right? You never know what you need to check for, spot the difference or die, kind of. Yeah. No, this is absolutely a valid point. All right, let's hop into perspectives, and then, of course, if we have time for more questions afterwards, we'll you can ask more. So to kind of try to loop all the way back to where I started, the question of what is an explanation is unfortunately unanswered, and I would say that it's unanswered in all of the sciences. And to the degree that the different sciences or different fields have a good answer to this, the answers are not going to match. For instance, I found actually a text, a philosophical text by a guy who said in 1986 that this here is what an explanation is, okay? Or when you explain something, what you do is that you provide some information about an event's causal history. In an act of explaining, someone who is in possession of some information about the causal history of some event, explanatory information I should call it, tries to convey it to somebody else. Okay, yes, that's absolutely very nice. But can we translate this to machine learning or neural networks at all? I would say that if we even try to do that, then, okay, well, what is the causal history, of a model or of data? If I wanted to make that whole story, then I would have to tell somebody about either, like, how the data came about and how it traveled through the neural network. Here, it was multiplied by this, and then it was multiplied by that. Or perhaps I even would have to tell a story about, how the data came about, how the model was trained and everything. And unfortunately, I don't think that people would be interested in that. I could tell the longest causal story in the universe about my machine learning model, but I don't think that most people would care. So I think that there's definitely stuff to be had, as always, from philosophy. But I think that we need to at least also, if not instead, go to the social sciences to try to find out what people want from our explanations. And the fantastic thing is that this marvelous guy called Tim Miller, he's a professor somewhere in Australia. He, 1 year when he was on sabbatical, he sat down and he wrote the most comprehensive paper ever on XAI and how explanations should look. It's called Explanations in AI Insights from the Social Sciences, and I urge you to read it. It's an easy read, and it's a pleasurable read. He writes very well, and also what he does is that throughout the paper, he really tells you, like, these are the insights here that I have found, and he condenses it really nicely. So this paper is not something he's written to show off how clever he is, but really to inform people. And one thing that he writes really early, his main finding, is that explanations are not just the presentation of associations and causes, they're also contextual, okay? So when you give an explanation, you have to take the context into account that an event has taken place or something has happened and that the person receiving the explanation is in. And this fits also very well with what Hilton said in 1990, was that the key insight is to recognize that one does not explain events, singular, isolated events per se, but then one explains why the puzzling event occurred in the target cases, but not in some counterfactual case. And if you're like, what does she mean by that? Then think about if you go somewhere and ask a machine learning model, what should I do in this case, or what is the prediction in this case? If the prediction surprises you, then you would want to know what is different in this situation, or what makes this situation different from a situation in which I will get an outcome that didn't surprise me, okay? And this is also one of Tim Miller's conclusions or main points from this spectacular paper, is that when you make an explanation, you have to contrast it to something. You can't just go like, here isolated, this is what's going on. People kind of need some hook or some situation to compare to that they also expected or also didn't expect. And this brings us on to a kind of explanation that I wasn't really sure where to put in this lecture, but that I've realized that we kind of can't go without because it's one of the really huge trends right now within in the XAI literature, which is, I think, sparked by this paper by Tim Miller. And the paper is highly cited, highly influential. And it's a thing called counterfactual explanations. So counterfactual explanations are explanations where you tell somebody, the explainee, the recipient of the explanation, about the smallest change they could have made to the input or the situation that went into the model that would have caused a substantially different prediction by the model, right? So if it's a classification model, what would have caused the predicted class to change to a different class? And now if you have a decision tree and want to make such a counterfactual explanation, all you would have to do would be look at the latest split before the prediction, right? And go, if I flipped this, or what would I have to flip in order to end up in a different node and then with a different prediction? Unfortunately, with our best machine learning models, our neural networks, we can't do that. We can't stare at a neural network and go, oh, if I change this, this is going to change over there. No, unfortunately not. So then producing these counterfactual explanations of what would have to change in order to change the output becomes of an optimization problem. All right. So what you have to do if you want to generate counterfactual explanations now is basically optimize some function measuring the difference between the original output and the output that you had expected or would desire to get instead, and then constraining that search for a solution or that optimization problem to how big changes you can make to the input to the model. Okay. So the first, I think, time that this was formulated in the XAI literature was in 2017, where they said that, okay, in order to generate counterfactual explanations, this is the loss that you have to minimize. Okay, and there are just two terms in here, so that's pretty intuitive. So first, you have to make sure that the distance between the instance that actually went into the model, so the instance that you want to explain to somebody, that the distance between this one and the counterfactual case, the other case that would change the outcome, that this distance is small. Okay, because you don't want to tell somebody that they have to make a huge change, right? So search kind of in the vicinity of the original instance. And at the same time, the distance between the actual prediction of the model and the desired outcome, so the expected outcome, or what whoever went into the model would instead want the model to say, should also be small, right? Because you want to tell them something about what they have to do in order to approach the outcome that they were expecting, right? If I say, why isn't it green, and I start telling you about like what you would have to do to make it blue, then you wouldn't be very happy. Okay, so there are two distances here that need to be minimized. But let's go back to the classic example that I told you about yesterday. A person goes to the bank, applies for a loan, and the computer at the bank says, no, you don't get the loan. Then the actual case here is computer says no, but the counterfactual case, so the case that you desired or expected, that was computer says yes, right? That's what we want. So here we have a prediction y, which is no, and then a prediction y prime, which is yes. And now I would like to know what I have to change in my input x in order to instead get prediction y prime. Then I can produce, if I go and do this huge search for counterfactual instances x prime, right, then I could end up with a long list of stuff that would make the computer say yes. It could be increase your income by, 1,000, but it could also be change your gender, or it could be move to a different state, switch job, get married, get a dog, right? You can change a lot of things in the input and arrive at a different prediction. But not all of these would be like very satisfying or very actionable even. Like changing your gender, I don't think you can ask people to do that in order to get a loan. So counterfactual explanations reloaded kind of became that instead of only the two objectives that we had in the previous loss to be minimized that I showed you, we actually need 4. Okay, so the first one is still what the second one was earlier, that the new prediction on the counterfactual x prime should be as close to the expected prediction as possible, okay? Also, the counterfactual x prime should be as similar as possible to your original instance, okay? So those are still good. But also, the counterfactual, so the situation I tell that you have to change into, should involve a sparse change in the actual instance, right? So instead of telling you to move your house 2 meters to the right and also, get married again and get a dog, I just say, okay, so this is the one major thing that you have to change. And if you change this one thing, then the outcome is going to get closer to the outcome that you want. Okay, so sparse changes in the input data. Also, the counterfactual, and I think this is so important, should be likely, right? So saying something like, you can remain who you are, but you need to change your gender, that is very unlikely, right? So into this, this loss here that you minimize when looking for the counterfactual explanations, you should have some real world observations, capital X, that tell you about which instances can we sort of ask people to try to turn into. Okay, and this is, as far as I know, now I don't work on counterfactuals, but this is, as far as I know, the kind of state of the art when searching for counterfactual explanations, is this huge loss with 4 terms that all have to be optimized at the same time. So I'm curious, I want to ask you guys, do you think that explanations given about a machine learning model, and we all know machine learning models, right? They do correlation detection. Do you guys think that these explanations should be founded in causality? What do you think? Yes? A few? I like you have like a strong opinion hand, like yes. Yes, exactly, I like that. How many say no? So most of you just don't have an opinion, no? Didn't understand the question? Really tired? Voted blank? There's a lot of hands that didn't go up at all. Okay. Come tell me afterwards what you're thinking about this. So the funny thing is that both this Miller paper that I'm absolutely in love with and another, I think Holzinger is a psychologist, I'm not sure, argue that yes, explanations must be founded in causality. And I kind of like get it, because you want to tell people that you explain stuff to, you want to tell them stories about the real world, because we live in the real world, right? But if we agree that explanations have to be founded in causality, then XAI methods need to be not only accurate, complete, relevant, contextual, and all that, but they also need to consider the data generating process, right? So the stuff that happened before the data was even collected and delivered and the model was trained. So then that's going to be a lot of work, right? If we have to take the whole like causal history of, not the causal history, but yeah, the whole data generating process of the real world into account when we make our XAI methods. But it kind of also makes sense, because let's go back to the classical example again that has certainly become a classic now today. So I apply for a loan, computer says no, and the counterfactual explanation that has been optimized out for me is that you need a higher income. Okay, if you get a higher income, you get this loan. But then what happens if I get a higher income? I'm going to get higher expenses as well, right? I get a higher income, sweet, new car, new, I don't know, new friends, more salmon. So giving me a higher income would probably change, my whole behavior. It would not only affect my savings account, it would affect very many different aspects of my life. And then maybe I could go back to the bank with a higher income, but then all my other features that describe me as a person will also have changed. And what then? Then probably the explanation isn't going to be accurate anymore, right? So in order to make kind of causal XAI, if you want to, we have to appreciate the challenge that while the place where data is generated is the real world, where we have confounders and exposures, and we can find out what influences the outcome by making interventions and so on. But that is not the place where features live. Like our data feature that we train models on, they kind of live in like a layer below reality, if you will. If you go and intervene upon a feature, then the other features in the data set don't care, right? So if you want to make interventions, you have to go like a step up from where the data lives, and then you might have to collect new data. So then the question then becomes that if we want to make XAI methods that are somehow based in causality, then kind of where should we go and change things? Should we say we just have to stop doing statistical learning at all? We have to do some kind of causal learning, and then on top of that we can generate explanations. Or can we continue doing statistical learning, and then have the XAI methods, but then feed the XAI methods themselves, with the causal graph, so that the explanation methods know about the causal connections? Or should we do statistical learning, generate counterfactuals, and then add a new term to this optimization problem that makes sure that the counterfactual explanations take any changes into account that would happen if you follow that. So it kind of becomes a bit of a nightmare, right? And obviously there is a lot of literature, and there is this well-developed, mature language out there that we can use in order to talk about causality and causal modeling. And there is this review that has tried to kind of see how that can be adopted into the development of XAI method. It's called Causal Explanations in XAI. It was published last year. And basically what the author says, I think one sentence just sums up the conclusion of that paper beautifully. There's a library literature on how to define actual causation using causal models, but this literature has yet to find its way into the XAI literature. So kind of causal XAI is something that I'm looking at it together with a PhD student, but it's just not obvious at all where you should, kind of start. So I would say this might be the most immature part of XAI that we have at all. But what we do know is that people care about the real world. People do not care about our models, right? So somehow we will have to stuff causality into our XAI methods. And I'm just really excited to see how we're going to do that. So finally, before I let you go, this is like a personal little pet peeve of mine, and this is also something that I think I'm going to take with me into the ethics panel discussion that we're going to have on Friday. We know that when we explain stuff to people, like if you're being honest with yourself, when you explain stuff to people, your intention isn't always explaining to them what happened, right? You probably always, every time you explain something to somebody, you have some other intention also in mind, right? You want them to learn something that you've learned, so you want them to kind of share your opinion, your view of the world. You want to assign blame to somebody else than yourself. You want to persuade people, right? So I don't think that we can kind of disregard this social aspect of explanations, that they always have some other intention than just explaining things. And I recently published a passive-aggressive preprint with some friends where we argued that explanations that we create from machine learning models, very often we see now in the real world, have the intention of justification or diversion. So now I'm so immature and old at the same time that I'm gonna hate on Facebook. Sometimes the ads that you get on Facebook seem like weirdly relevant or weirdly irrelevant, and then you can click on the three little dots and you can go, why am I seeing this ad? And then you're supposed to get an explanation for it. And then the explanation is usually correct. It says something like, yeah, so it's because you're in this age group, and you are in this age group, but you feel like that only seems true, but it doesn't seem like the honest explanation at all. Or even sometimes just the reason that the explanation is not available. That's also a funny one. But I'm afraid that very often there is something, when we receive simple explanations for what's going on in the world, I'm always worried that there is something else underneath. And the truth is that there is now a huge part of the machine learning literature available that shows us that based on non-privacy protected data, you can find out very much about people's mental states, mental illnesses, vulnerabilities, and I think it's pretty naive if we assume that if that information is out there and it's being fed into machine learning models whose purpose is basically to sell us things or to persuade us, affect our behavior, then I think it's pretty naive that we believe that extracted information about our mental vulnerabilities isn't being used, So I think an honest explanation about, for instance, why you're seeing this ad would contain something like, well, you have low impulse control usually when you scroll like this. and not, age. No, so you're laughing, I'm crying. No, it really worries me right now that the direction that we're going with the explanations is more in the direction of persuasion or justification or diversion, and not necessarily honesty. Because, think about it. Now, what is intelligence really? Come on, it's the ability to solve problems or to achieve goals. If we give our XAI methods the goal of being convincing to humans, right? Providing a convincing explanation can be a goal, and we make very intelligent models that are capable of basically delivering explanations that convince us, then I think that our autonomy is really in for a kind of ride that it doesn't want to be in for. So every time you generate an explanation, what you basically do, right, is that you extract some information. You can't tell the whole story about a model in an explanation, so you have to leave out some information. A question about which information you can leave out, it's a bit of a delicate one, right? And I'm not even sure of how we should answer that question. What information is it okay for me to leave out and still kind of being able to call the explanation complete or honest? Now, my favorite kind of insight from statistics is that all models are wrong, but some are useful. Like, no model completely equals reality, and we all agree on that, that's fine. But I think we should take that insight one step further and realize that no explanation of a model equals the model itself. You always have to leave out some information, and the question is, what information can we leave out, and when? And that's all I had for you, basically. So, thanks a lot. And we have plenty of time for questions.
Yes. Questions.
Questions or die.
Questions.
Hello, okay.
Yeah.
So about the causality remark, I think causality and explanations tend to answer the same sort of question. So why something happened and what really contributed to a certain outcome. But an important distinction, I would say, is that when you do explanation, usually you're interested in model explanation, while causality instead tries to look at the data. So what are you trying to explain? Are you trying to explain model or are you trying to explain data? And I think that there is a close connection between the two, and you could think of the data, if you think of the data generating process, and the model is an approximation of your data generating process, then perhaps there is an additional noise between explaining model and explaining data. And yeah, I wonder what's your opinion about that, and if you have something to add.
Yeah, that's an excellent question. So I would say that if we knew that our machine learning models were a good kind of an approximation or a story about the data generating process, then there would be kind of no divide here. Because then if the model was that, a good description of the DGP, then I could put my XAI method on top of that and say, now this helps me to explain the DGP and what the model got out of it, okay? But then we wouldn't be doing the kind of machine learning that we do now that is effectively correlation detection, right? Then we would kind of switch to doing some kind of causal learning and then putting explanations on top of that. Right now, unfortunately, our models do correlation detection, right? So if we want any causality in here, then that has to be either on the explanation, the XAI method, or we have to do modeling in a different way. But apart from that, I absolutely agree with your reasoning.
Yeah. So one question, what do you say about sort of more an HCI perspective on what an explanation is? Essentially saying an explanation is something that allows the user to build a mental model of whatever their system did. And now, of course, comes the tricky part that is adequate for him to solve whatever he's trying to solve using the system, right? I mean, that's where with the car. Nobody really understands how the car works, right? People have a model, mental model, that's usually wrong. As you say, all models are wrong. But it is adequate for most people to drive the car without killing themselves too often, right? So that would be the definition for me of explainability.
Yes, and I agree with that to a huge extent. Now, the challenge is that cars aren't a high-dimensional phenomena, right? A car doesn't have a million dimension in which unexpected things can happen and things can go wrong, right? So to me, that is like the crucial difference between a mechanical machine in our world that we can have some intuition for, right, and a model that lives in a million-dimensional space and where we just kind of don't know what's going on.
I agree with that. Just, we're talking about the aim of the model, right? So the idea of the aim is not causality or anything. The aim is to provide the user, and the user is somebody defined who wants to achieve a specific goal with the system, a mental model that helps him actually achieve that goal, right? Mm. It's sort of like an HCI-ish definition that you would have for many things.
Yeah, and then you would have to take the interest of the person or the goals of the person into account when you generate the explanations.
Sure.
Yeah, so the closest you would get then, I would say, are counterfactuals. Right? What does the model do? What do you want? Let's see if we can make this happen. Yeah.
My question is about, do you think that if XAI for roboticists, it could be a very good selling point that, for example, we are putting a black box system in applications, in robots that are being used in applications that are being used with the people in quite vulnerable situations. So do you think that the risk assessment should be part of the explainability, or this is not the concept that XAI should have to deal with when it comes to the machine learning systems in the robotics?
Yeah, so my personal take is that it should be the reverse, that the explanation should be part of the risk assessment. The other way. But yeah, I think the more safety critical applications you have, the more important it is for you to understand the system. And so I worked with robotics for a year, and the motivation that I kind of always faced was robustness. Like, can I know that the system is going to behave robustly in like any situation that it's going to end up with? And then, I don't know, were you here yesterday? Yeah, so then I showed the real life adversarial attack example, right? You can't come up with, or you can't conceive of every situation that you should test for, right? So I kind of argued against a test-based approach to robustness, and then I think the only thing you're left with is explaining your way to robustness, right? So I would say definitely yes.
More questions, comments?
Thanks. So I was wondering if there's a specific XAI techniques for large language models that we should look at.
Language models?
Yes.
Sorry, I don't know. I wish I knew. No, language model and time series like next on my list. But then came diffusion models from the side, and I'm just all distracted. And I'm not even kidding.
Thanks. One other remark, and if I can, about the methods SHAP in particular. I would love to discuss with you a possible critique to the method, which is SHAP is the only method that satisfies all three properties, like symmetry, dummy, and efficiency. And arguably, efficiency is the most important one among the three. Or at least, arguably then. But it's a very relevant one, and people look out for it. And however, if you think about it, a Shapley value has an importance only when it's relative to the other Shapley values that you have. So as an absolute number, it doesn't tell you much. And under this perspective, you might think that actually efficiency, who cares? I could just take the values that I get, whatever they are, normalize it, and get the total amount that I want. So, and if we think in this perspective, then who cares about Shapley? Like, I could literally use any distribution over my coalition, and that would be fine, because I don't really need the three properties. Yeah, maybe what do you think about that?
Yeah, so I would say efficiency is important because if you don't have it, then all the SHAP values in this case, SHAP values aren't going to sum up to the model prediction, right? So then you haven't accounted for the whole model prediction. You can of course say I'm going to normalize, right? I'm going to pretend the model prediction is always 1, right? And then how much in something that looks like a percentage does each feature contribute? Yeah, and then from that you went on to say something like I could argue against every property, and none of the properties are important, so why would I care about the SHAP decomposition?
No, I was like, then you don't need any more SHAP necessarily because you don't need the uniqueness, since efficiency maybe we could argue is not that important.
Yeah, and symmetry isn't as important and so why would I care?
And the dummy makes sense, but I was just saying perhaps this efficiency is not relevant because you can somehow normalize and you get the same effect.
Mm-hmm.
Then,
and there are indeed solution concepts in the game theory literature where you don't have to evaluate as many terms, so that are computationally a lot more approachable, that I would say are just as favorable, like Peter Zank value, I think it's called, and then I actually have a preprint going on right now, but I don't remember it, where we argued that there are other solution concepts that you could use from game theory that give you just as good kind of future importance attributions scores that are less computationally heavy to calculate, and that don't have some of these axiomatic properties, because, well, you know, yeah, maybe you wouldn't be interested in them, or maybe they're not that important to you. Now you're touching upon something that is really interesting, and that is that the XAI literature has kind of argued that the Shapley decomposition is very favorable because it is provably the only solution concept that satisfies these axioms, right? But we haven't really kind of taken the step back and argued why these axioms are favorable or important to us in the first place, right? So I think you're making a good point that we could take a step back and ask, which of these axioms do we really need to satisfy? Yeah, good comment, thank you.
Any more questions, comments, discussion?
What you can do is also stretch your legs for 5 minutes, because there's another lecture afterwards, right?
Yeah. So,
yeah, go stretch your legs.
Yeah,
Jeez,
yeah,
I'm going to be here all week.
Yeah, no. So,
Right.
so this was Inga's last talk, but she will be around. So if you want to have more discussions with her, she will be available. So I think let us thank her, and then we take a short break while we set up the next speaker.